Now in this session we are going to see with the module 5 material science semiconductors. Till now we have seen the conductors, material science in conductors. Now we go with the semiconductors. Now what is the physics of semiconductors? Now energy level diagrams for a metal, semiconductor and insulators. Now you can see the energy level diagram here. Conduction band and valence band are totally overlapped in the metals, and in the semiconductors the energy gap, valence band and conduction band, there is a small energy gap. But in the case of insulator there is a large energy gap, e.g. that means valence band and conduction band are very far apart with the difference in the gap called as energy gap. So this is the difference, the energy level diagram for a metal, semiconductors and insulators. Now conductivity of in a semiconductor, the conductivity is happening because of electrons as well as for holes. What are n-type semiconductors and what are p-type semiconductors, and conductivity of n-type semiconductors, how it is there, and conductivity of p-type, what exactly is a p-type semiconductor and what exactly is an n-type semiconductor. Conductivity of an n-type semiconductor, in an n-type semiconductor majority is the electrons. So the electron concentration is far greater than the hole concentration. Therefore sigma is equal to Ne E mu plus Nh E mu. That means Ne is the concentration of electrons, Nh is the concentration of holes. In an n-type semiconductor we know that majority charge carriers of electrons, therefore Ne is greater than Nh or the holes. So sigma is equal to Ne mu E into E. Conductivity of a p-type semiconductor, it is nothing but the hole concentration is far greater than the electron concentration. So here we have taken as Ne E mu plus Nh E mu. Here number of holes are more, therefore number of holes p-type, it is Np is greater than Ne, therefore mu h, sigma h is equal to Nh E into h. Here in an n-type semiconductor conductivity is because of electrons, and in a p-type semiconductor electrons are nothing but majority carriers are holes. So conductivity in an n-type semiconductor is because of electrons, and conductivity in p-type semiconductors is because of the holes. Now we are going to derive the expression for an electrical conductivity of a semiconductor. Here in a semiconductor we have seen that the conductivity is because of electrons as well as the holes. In a semiconductor the net current is due to both electrons and holes. The current due to electrons is IE, it is NeAVE. That means Ne is the number density of electrons, the number of electrons, A is the area, V is the drift velocity and E is the charge. V is the drift velocity of the electrons. The current due to holes IH is equal to NHAEVH. Here because of the holes, number of NH is nothing but the number of holes. The total current I is equal to IE plus IH. So taking the equations related to IE and IH, if you add it, EA into NEVE plus NHVH. But we know that I by A is nothing but J. Taking the values common here, rearranging the terms, J is nothing but I by A. Rearranging the terms, we get J is equal to E into NEVE plus NHVH. J is nothing but the current density. So we get J is equal to E into NEVE plus NHVH. If you look at this equation here, J is nothing but I by A, the same equation we are writing here. J is equal to E into NEVE plus NH into VH. But we know that J is equal to sigma E. I have defined the equations before the starting in this module. So J is equal to sigma E. So sigma E, J can be written as sigma E and the RHS remains the same. So sigma E, we know that sigma E can be taken here. Rearranging the terms, bring this to the RHS. So sigma is equal to E NE into VE by E plus NH into VH by E. As we know, the drift velocity is equal to mu into E. Rewriting this equation, VE by E can be taken as mu E and mu H. Substituting the value of mu E and mu H into this equation, sigma is equal to E into NE mu E plus NH into mu H. So this conductivity in a semiconductor is nothing but E into Ne mu E plus NH into mu H, where mu E and mu H are the mobilities of the electrons and the holes respectively. For an intrinsic semiconductor, Ne is equal to NH is equal to Ni. What is an intrinsic semiconductor? Which is a pure semiconductor where there is no doping at all. So number of electrons is equal to number of holes. It is a pure semiconductor. So Ne is equal to number of electrons is equal to number of holes in an intrinsic semiconductor, which is nothing but a pure semiconductor. So it is called as a density of intrinsic charge carriers. So rearranging, then sigma is equal to E into Ni mu E plus mu H. So this is the expression for a semiconductor, the conductivity of a semiconductor. We have derived the expression that current in a semiconductor is because of electron current and the hole current. So this sigma is equal to E Ni into mu E plus mu H, where Ni is the intrinsic charge carriers. Now what is the expression for the electron concentration Ne and the expression for the hole concentration NH? Here Ne and NH, you have to remember very carefully that in a semiconductor, Ne is the number of electrons, where it is electrons are lying in the conduction band and holes are lying in the valence band. So electron concentration Ne is taken in the conduction band. Always try to remember that electrons tries to occupy the conduction band, where electrons are free to move in the conduction band, leading to the current, leading to the conductivity because of electrons in the movement of electrons in the conduction band, whereas holes move in the valence band. So the number of electrons in the conduction band per unit volume of a material is called as electron concentration. Though you do not have a derivation for this, but you need to remember the expressions. These expressions are useful for the next derivations. In the next session, in the next video, we have to use these two expressions. So before going to start with the expressions or the derivations, you need to have these expressions. Using these expressions, we are going to derive something else. So this becomes the basis. So what is electron concentration is number of electrons in the conduction band per unit volume of a material is called as a electron concentration. As I told you earlier, the electrons, the number of electrons in the conduction band per unit volume of a material is called as a electron concentration. Remember, electrons always move in the conduction band, whereas holes move in the valence band. Now expression for the hole concentration. The number of holes in the valence band per unit volume of a material is called as a hole concentration. So NH is equal to 4 root 2 pi mH star KT by H square into root whole to the power of 3 by 2 into e to the power of minus EF by KT. If you look at the expressions, these expressions are little tricky to understand, or since you do not have the derivation, please try to remember in a logical way. I'll give you a small tip for this. See here, Ne is equal to 4 root 2. Pi me star kt by h square. This remains constant for both the equations Ne and NH to the power of 3 by 2. The only thing you have to remember is here in Ne, EF minus Eg by kt, and here it is E to the power of EF by kt. EF minus Eg by kt, and here it is EF by kt. Only the difference is minus Eg has come extra in the electron concentration. Always try to remember, in a semiconductor there is an energy gap between the valence band and the conduction band. Conduction band is at a higher energy level and valence band is at a lower level. So here always try to remember, when an electron moves to a conduction band, a hole is created in the valence band. So the hole is moving in the valence band, and the electron, it has moved from valence band to the conduction band, crossing the energy gap as the temperature is increased. Therefore, electron is free to move in the conduction current, leading to the electron current, and the vacant space left out by an electron in the valence band is nothing but a hole. Since the hole is moving in the valence band, holes move in the valence band constitute hole current. So this is the electron current and the hole current. Thank you.